So, thanks for the opportunity to present today. I'll start right away with a short outline of this talk. First, I will talk about why we even did this study and why particle number concentration measurements during periodic technical inspections are relevant at all. Then I will briefly introduce the methods we used. So this includes experimental methods and the setup and the evaluation methods we employed. Then I will show some results on particle number concentrations and size distributions and the evaluation of particle number measurement instrument specifications. And then I will talk a little about the impact assessment we did, and I will close with a short introduction. So first, the relevance of the particle number measurements in PTI. So a recent study by Bouveroux et al. Investigated more than 300 light-duty Euro 5 and Euro 6 diesel vehicles, and they found that only 15% of the vehicles caused more than 97% of the fleet particle emissions. And these high emissions were predominantly caused by malfunction after treatment system, especially broken DPFs. So this is why it's relevant for light-duty vehicles, and for heavy-duty vehicles. Additionally, DPFs are often removed for improved fuel economy. So this additionally increases the fleet emissions by only a small number of vehicles with these DPFs removed. So the identification of the small number of high emitters can drastically decrease and reduce the fleet emissions, and therefore can have a positive impact on the air quality. And the currently employed method is usually opacity measurements, and it has been shown repeatedly that this method is not sufficient for a reliable identification of the high emitters, but particle number concentration measurements in low idle speed has been shown to be an effective tool for the reliable identification. And the reason for that is that the particle number concentration regimes of the exhaust of vehicles with intact DPFs and broken DPFs are separated by more than one order of magnitude in particle number concentration. So the exhaust of a vehicle with a broken DPF usually exhibits more than 1 million particles per cubic centimeter, and the exhaust of a vehicle with an intact DPF will have less than 50,000 particles per cubic centimeter. So different working groups proposed a threshold value in between these two values with 250,000 particles per cubic centimeter. And by doing simple math, it turns out that if you use a particle number concentration measurement, this instrument has to overestimate the particle number concentration less than 400% and underestimate it less than minus 75% in order to reliably discriminate between intact DPF and broken DPF, and hence categorize in low and high emitters. So what is the aim of this study? In this study, we tested prototype particle number instruments and compared them with lab equipment, so PMP compliant measurement equipment, and validated the categorization into high and low emitters. And we evaluated under discussion instrument specifications. For that, we collected size distribution data of vehicles in idle speed and evaluated the respective counting efficiency limits with this data. And last but not least, we performed an impact assessment of PTI measurements, because while it's common sense in the scientific community that the impact can be substantial of these measurements during PTI, nobody really put a number to this and showed how high the impact can be. So we made simulations taking into account different scenarios of DPF aging, fleet, vehicle age distribution, and different PTI schedules that are prescribed in different countries. So now we'll briefly show the methods we used. So in our measurement campaign, we measured the particle number concentrations and size distributions of 21 vehicles in low and high idle speed. And because of the limited time today, I will only focus on the diesel vehicles we measured. Were 15 vehicles and 10 of them were equipped with particle filters. For the particle number concentration measurement, we used 3 prototype diffusion chargers, which differed in some technical details. And as a reference instrument, we used the AVIL APC, which is a PMP compliant instrument. For the size distribution measurement, we used the SMPS for high size resolution and an EAPS for high temporal resolution. Before our actual measurements, we did a set of calibration measurements with an aerosol generator. We used the Pallas graphite spark generator for this. And as mentioned before, we measured the particle properties and concentrations of the vehicles in low and high idle speed. Now for the evaluation of the instrument specifications, we evaluated different of these regulations, starting with the well-known PMP regulation for type approval measurements. What you can see here is on the x-axis the particle diameter, and the colored area is the compliance region, which is rather strict for the PMP. And we also evaluated the RDE specifications for mobile emission measurements. And in addition to that, also the VAMV, which is the Swiss regulation for construction machinery and ships. And last but not least, we also evaluated the specifications elaborated by the VERT and PTI working group. And to evaluate the effectiveness of these counting efficiency limits, we took our particle size distribution data and multiplied this size distribution with the lower and upper limits of these colored areas here to get a weighting function. And then by integrating over all particle diameters, we get a maximal under and overestimation. So this is briefly illustrated here with a typical diesel particle size distribution with a GMD of 17 nanometer and a GSD of 1.7 for the lower limit, so the maximal under estimation, and here for upper limit, maximum overestimation. And you can see for this typical size distribution, maximum underestimation is close to 50%, and maximum overestimation exceeds 50% a little. Yeah. Now for the results. As mentioned, we measured particle number concentration and saw if we could identify the vehicles with an intact DPF, which are indicated by boxes around them here in the diagrams. And we did that in low and high idle. And as you can see, as we expected with all particle number measurement instruments employed, we could reliably say from the results which are equipped with DPF and which are not, just by looking if they exceed this threshold value I introduced before of 250,000 particles per cubic centimeter, with one exception where we had a technical issue with moisture in the lines from a different measurement before. But in general, we are pretty happy with that. And now for the particle size distributions. So we evaluated the size distributions of the measurement points where we had enough signal to in the SMPS to perform unimodal log number of fits. And you can see here in this diagram where the x-axis shows the GMD of the size distribution and the GSD is on the y-axis, that the measurement points are recorded in high idle and low idle form distinct clusters with the larger sizes for the measurement points in low idle. And we think that this is related to the longer residence time in the cylinder where the particle concentration is high, so a longer residence time there would lead to more agglomeration and finally larger particles, which, yeah, we measure in low idle. And now for the evaluation of the instrument specifications, what you can see here now is for the overestimation. It's basically the same plot as before. So the x-axis is again GMD and the y-axis a GSD, but now there's a third axis which shows the deviation. And this black area indicates this 400% threshold I introduced before, which should not be exceeded for, to exclude bad scenarios. And as you can see here, the points indicate that we are pretty far off of this threshold value for all specifications evaluated. And yeah, there are basically no critical cases. And all specifications effectively guarantee the exclusion of false fail scenarios. With the underestimation, things are a little more critical. So this is the same plot as before, but now for the underestimation. And what you can see with the black surface here is the -75% threshold, which should not be exceeded. And you can see that the smaller particle sizes in the high idle measurements raise the risk of false pass scenarios in extreme scenarios, which is especially relevant for the VAMV and the NPTI specifications. So we would recommend to perform measurements in low idle, although the constructed scenarios here are somewhat academic and very extreme, but you can achieve more measurement accuracy performing tests in low idle without mandating stricter specifications. And now, finally, I will come to the impact assessment. So what we did here, we basically calculated the reduction of time in circulation with broken DPFs by introducing PTI and the measurements of the particle number concentration during this PTI for the identification of high emitters. And for the impact assessment, we took into account different PTI schedules of Germany, Belgium, and the Netherlands, which are the countries that will introduce this kind of measurements soon, or some of them already did. Then we took into account different fleet age distributions and also DPF probability density function as a function of time. We evaluated 45 different scenarios, so all combinations of these, and I will just show the results of this very briefly. What we can see is that according to our calculations, the maximum reduction that can be expected is 83%, and the most pessimistic scenario predicts a reduction of 60%. And the DPF aging behavior is largely unknown, but we can see that limited that the influence of this behavior is rather limited on the reduction of the overall emissions. And by comparing the German and the Dutch schedules, we can see that doubling the PTI frequency would yield another 50% further reduction in overall emissions. Now let me conclude my talk. So we showed that we could identify high emitters, so vehicles without DPFs, even with rather low-cost equipment. For diesel vehicles, we had some issues with gasoline vehicles, but yeah, this wasn't covered in this talk today. And we saw that the under discussion specifications are effective for the expected size distributions, but we nevertheless would recommend to perform tests in low idle speed to increase the particle size and get more accuracy without mandating stricter limits. And our impact assessment showed that the fleet emission reduction, which is achievable by the introduction of PN measurements during PTI, can even exceed 80%. This, say thank you. Open for questions now.
Thank you so much. If there are any questions on your raised hand section, if not, I'm sure to pop up in the chat, and Markus will be able to answer there as well. All right, I'm not seeing any, so we will go on to our next speaker. So thank you so much, Markus.
Thank you.